In today's lesson, we are going to learn about acid dissociation constant Ka. As we know, weak acids dissociate partially or slightly in water to produce a low concentration of hydronium ions. The dissociation of weak acid in water can be represented in the equation shown. For a weak acid Ha, which dissociates slightly in water to produce hydronium ions and A negative ions. The acid dissociation constant Ka for the weak acid given can be expressed as the product of the concentration of hydronium ions and the concentration of A negative ions divided by the concentration of the weak acid Ha. Let us look at an example. For a weak acid, hydrogen cyanide is shown in the equation. How would you write the Ka expression? Yes, Ka can be written as the product of the concentration of hydronium ions and cyanide ions Cn negative divided by the concentration of weak acid hydrogen cyanide. There are a few points that we should keep in mind. A stronger acid has a higher concentration of hydronium ions and therefore a larger Ka value. A smaller Ka value indicates that there is a lower percent of weak acid dissociated and therefore is a weaker acid. Generally, weak acids have Ka values, or weak acids have their own acid dissociation constants Ka. What about strong acids? Does strong acid have Ka values? For strong acids and bases, the dissociation in water is 100%, and therefore the Ka or Kb values have not been measured. So there are no Ka or Kb values for strong acids and bases. Similar to weak acids having Ka values, weak bases have Kb values. The dissociation of a weak base in water can be represented in the equation shown. For a weak base B dissociates partially in water to produce ions BH plus and hydroxide ions. The base dissociation constant Kb can be written as the product of the concentration of BH plus ions and hydroxide ions divided by the concentration of the weak base B. Let us look at an example. For the dissociation of a weak base ammonia, ammonia dissociates partially in water to produce ammonium ions and hydroxide ions. The expression of Kb can be written as the product of the concentration of ammonium ions NH4 plus and hydroxide ions divided by the concentration of the weak base ammonia. Now, let us see what is the relationship between Ka and pKa. pKa equals to the negative logarithm of the Ka value. As shown in the table, the Ka and pKa values for various acids are given. As it can be seen that a higher Ka value has a lower pKa. For example, by referring to the acid with the highest Ka, which is hydrogen sulfate ion, has the highest Ka value and the lowest pKa value. A larger Ka represents a higher acidity. Let us look at the relationship between Kb and pKb. pKb equals to the negative logarithm of the Kb value. In the table, it is shown the Kb and pKb values for various weak bases. It is seen that the base with the highest Kb value has the lowest pKb value. For example, from the table it is seen that ammonia has the highest Kb value and the lowest pKb value. Therefore, a high Kb has a low pKb value. So it can be said that a larger Kb represents a higher basicity. As we know, weak acid and weak bases dissociate slightly or partially in an aqueous solution, and therefore the degree of dissociation can be calculated. The degree of dissociation is also called the degree of ionization and is given the symbol alpha. The formula to calculate the degree of ionization is the fraction of the ionized acid concentration at equilibrium X to the initial concentration of the acid. In terms of percent ionization or percent dissociation, it also can be calculated as a fraction of the ionized acid concentration at equilibrium X to the initial concentration of the acid multiplied by 100%.